Hello everyone, it's Peter. Welcome you back. So in this session, I will start the basic Java programming training. I think some of you may be already a good Java programmer, and some of you may be a beginner. You may not use Java before, or you already write a lot of Java code. But in any case, I still strongly suggest you to go through this session. You may find something new, something you don't know, and something very important. So let's talk about some topics I will cover in this session. The first one is binary and hexadecimal representation of data. Since I say hex and the binary. As a CS major, this is mandatory, but for lots of people who are not from CS major, you just want to start the coding career, this is not that important. But from my experience, if you want to go to very deep, go to a high level of a programmer, maybe you want to move to the senior level or architectural level, I think this binary and the hex representation of data should be very, very important and helpful. The second one is Java language preferences. For those who already know Java programming, you can skip this session. So this is very basic. It will talk about some how to define variables, how to define an array, what's the data types in Java, and some tricky things. Maybe in your interview, may be helpful in your interview. And some condition or loop syntax like if else, switch, for loop, while loop, do while, etc. Okay. The next part is basic data structures. So if you want to solve some problem, I think data structure is very important. In this part, I will cover about like list structure, queue, stack, linked list, tree structure like binary tree, heap, and so on. And next is the algorithms. I also cover some basic algorithms like sorting algorithm, search algorithm like binary search, recursive algorithm, dynamic programming, DP. All of them are very basic, but if you are not from the CS major, I think this part may not be that easy for you. But if you are from CS major, those are basic things you must understand. Now, I may spend several sessions for those topics. Next, I will start the binary and the hexadecimal representation of data. Okay. So, in computer, in the memory, how does the computer store data? They use binary representation. So we start from a positive integer. I will use Notepad to show you how to represent the data. For example, if the data is like 5, so we can represent 5 in binary as 5. It can be divided as 2 as a 4 plus 1. 4 plus 1. 4 is 2 to the second power plus 1. So in binary is 1, 0, 1. Let's say binary code is 1, 0, 1. Okay. So, but in computer we don't write things in binary. In bits, we write things in bytes. So a full byte is 8 bit. So it's 0, 0, 0, 0, 0, 1, 0, 1. This is 5. It means that the last digit of 1 is 1. Then the second one is 2 to the second power is from 0. So this can be translated as starting from this one plus 0 times 2 plus 1 times 2 to the second power. So this one is this one, this 0 is this 0, and this one is for this one. So totally is 5. It's like our decimal. Our decimal, if you do any calculation of decimals, if you move to the 10, then you will have carry over to the upper digit. And for the binary, is if every time you move to 2, you will move to the next digit as a carryover. It's the same thing, but it's based on our habit. So if you always use the decimal, so this binary may be very new for you, but after you do some practice, you will get used to that. I'll give you another example. Suppose I have a binary code as 110101. So what is the decimal number? Okay. What is decimal number? So for this 110101, you can consider it as starting from the last one. Last one is 1. Right? One actually you can translate it as 1 times 2 to the 0th power. 2 to the 0th power is 0. Sorry, 2 to the 0th power is 1. Okay. Then plus 0 times 2 to the 1th power, right? This is the second 0. Then the third one is 1 times 2 to the second power, and plus 0 times 2 to the third power. Right? This 0. Then this one is 1 times 1 times 2 to the fourth power. And then another one, the first one is times 1 times 2 to the fifth power, which is 1. The second one is 0. Then it's 4. Then it's 0. Then it's 16. Then it's 32. So the whole number is this is 48, 52 is 53. This is 53. So you can translate it from a binary code to a decimal code, or you can from the decimal code to binary code. Okay. So this is binary representation. But the binary, one byte has 8 bits. It's too long. So we have a hex decimal code. Hex. I just simply say hex. Hex representation. The good thing is that hex is from 16. So if you add to 16, you have a carryover of 1. This is for hex. So every 4 binary bit is equal to 1 hexadecimal bit. So here I have a table here. This is 0 is 00000, 1 is 0001, and until 9. Hexadecimal 9 is 1001. The next, there's no 10. If we want to use one digit, then we use A, B, C, D, E, F. So A is 1010, B is 1011, C is 1100, D is 1101, E is 1110, and F is 1111. Okay. If you use F plus 1, then we'll move to high digit is 10. Okay. Now, let's come back to this example. For example, this one, if you go to the hex will become, I will rewrite it as I will add 2 zeros ahead. So I divide into 2 parts. The first one is 0011, the second is 0101. So hex is 3, 5. 3, 5 means what? 0011 from this table, 0011 from here is 3. And then 0101 from this table is 5. But after you get familiar with this translation between the binary to hex, so you should be very familiar with the translation. You can get the number immediately. So let's come back. So if we use hex to go to the decimal, that is 5 is 5, right? 3 means 3 times 16. So because in the hex, so every 16, it will move to upper digit for 1, right? So it's 3 times 16 plus 5 is equal to what? It's still equal to 53. It's the same answer as we use the binary calculation, okay? So this 48 plus 5 is 53. This is hex decimal. So to save the space, if we most of the time we don't really write a binary representation of a number. We can write a hex representation of a number. Okay, this is all about the positive. Now let's move to negative number. Negative number, for example, let's say negative 5. How to represent a negative 5? I still use 1 byte to represent it. So first we have 5 is 00000101. Okay. Now I flip it. Flip it is in Java. There's a sign called this one, tilde 5, which is change 1 to 0, change 0 to 1. Is flip each digit, then becomes 1 1 1 1 1 0 1 0. Then after that, I plus 1, and then I will become 1 1 1 1 1 0 1 1. This is -5. It's -5. It means if I want to find a negative number, then I first get a positive number, and I flip all the digits, then plus 1. Then this becomes a negative number. Okay. I give a very special example as -1. -1, how to do that? So first is 1, is 0 0 0 0 0 0 0 1, and then I flip it. I use this sign. Is 1 1 1 1 1 1 1 0. Then I plus 1. Then finally I get 1 1 1 1 1 1 1 1. If you use hexadecimal, is FF. This one I use hexadecimal is F. 1011 is what? 1011 is B. It means for -5, the binary representation is 11111011, and in hex code is FB. For -1, is 0000. Sorry, -1, the binary representation is 11111111. For the hex is FF. Is FF. So now I want to prove that in the code. So in this session, I mainly use the online compiler JDoodle. Now let's do it. Let's say I define int. Now int actually has 4 bytes. I will talk about later. But to explain the topic, explain the concept, I can use a byte or use int. So because of some Java language preference, I better use int. So int x equal to 5. Now I want to get the -5. Then I use y equal to, this is a bit operator. Tilde 5 is not 5, plus 1. Now let's print out x and y. X equals to x. Sorry. Maybe I can get it bigger. Okay, yeah, I make it bigger, and then plus y equals to plus 1. Let's run it. That's good. See, x equal to 5, y equal to -5. So here I introduce a sign. This sign is an operator to get to flip all binary digits. Yeah. This is this one. Okay. This, I can also call this as a NOT, but the logical NOT and the bit NOT is different. So we are talking about the bit operator. If you are very new to this binary and hex representation, you may watch this video several times to understand how to do that. Now let's come back. So we talk about binary representation of a positive and a negative number. Then we talk about the hex representation. Okay. Next, I will talk about the bit operator. So we have AND, or I just introduced this NOT, right? And this is exclusive OR. This is the bit operator, bit shift to the left, bit shift to the right. Okay. I will explain later. And then here I give some basic numbers, like 1 byte equal to 8 bits, equal to 2 hex. Right? 1 byte has 2 hex. And 1 hex equal to 4 bits. So that is 1 hex and 4 bits are 1-to-1 correspondence. Okay. 1 kilobyte is 2 to the 10th power of bytes, is 1024 bytes. And 1 megabyte is 1048576 bytes. Okay, so this is one megabyte is 2 to the 20th power, to the 20th power. Now let's come back to the bit operator, Okay. Now I will remove all of this. Okay. So first we talk about the bit operator AND. So the rule is this is AND. So we have 1, we have 0, we have 1. Okay. And we use 0. 0 and 0 is 0. 0 and 1 is 0. And 1 and 0 is 0. 1 and 1 is 1. So it means A and B equals to 1 if and only if A and B are both of them are 1. This is bit AND. It's bit AND. I want to clarify this is not a logical operators. If you know some logical operator like AND or not, this is quite different. I use a single AND. A single AND is a bit AND. Okay. So let's make an example. For example, let's say x equal to 5, which is byte operator is 0, 0, 0, 0, 1, 0, 1, 0, 1, and y is equal to 7. Let's give another one, 11. Okay. 11 is 0, 0, 0, 0, and 1, 0, 1, 1. Okay. So see this one, 1, 0, 1, 1. Okay. This is 10, this is 11. Okay. Now, if I do the AND operator for the two numbers, now I do AND x and y. Now let's see what happens. So I start from the first one, 0, 0, and 0 is 0. 0, 0, 0. So the 4 bit, there's no problem. The next one is 0 and 1. 0 and 1 is 0. 1 and 0 is 0. 0 and 1 is 0. And 1 and 1 is 1. So the answer is 1. Okay. So it means 5 and 11, they are 1. So let's prove that. Okay. X is 5, y is 11. Now c equals to 5 and x and y. Now let's see what is c. C equals to c. Okay. Now let's run it. C is equal to 1, right? We prove that. Okay. This is AND. Now after AND, AND has some basic rule is anything AND 0 is 0. Right? Because 0 is 0, 0, 0, 0. It's 8 bit are all zeros. So 0 and anything is 0. Okay. So this is one rule. And the second rule is that if you want to know the last bit, so x and 1 is the last digit of x. Okay. Last digit of x. For example, if x is 5, 5 is 0, 0, 0, 0, 0, 1, 0, 1. If you add 1, the first 7 digits are all 0. And only the last one is 1. So 1 and 1 is 1. If the last one is 0, then the answer is 0. If the last digit is 1, the answer is 1. Okay. So x and 1 is the last digit of x. And it can also identify this is an even or this is odd. Because if the last digit is 1, then this number is odd. If the last digit is 0, then the number is even. Is even. So we can use this condition to identify even or odd. Okay. This is about a bit. Now, next, I still want to use this example. I talk about the bit operator of O. and A or B equals to 1 if and only if A equals to 1 or B equals to 1 or both, or A equals to B equals to 1. All the three things is 1. So if I use all here, I use all here. 0 or 0 is 0. 0 or 1 is 1. This is 1. This is 1. It's this things. Okay. So if I use all to do the same operation, so 0, 1 here is 1. 1, 0 here is 1. 0, 1 here is 1. And 1 and 1 is 1. 1. This is FF, which is 15. Right? So let's prove that. If I use all, then let's see what is C. See, C is 15. This is bit operator of all. Yeah. Not difficult. I think based on this example, you understand what is bit operator and bit operator of all. Now, next is not. Not we already talked about that. It will go to the negative number. Okay, I already make an example. So I just want to skip not. Then I talk about exclusive all. This is very important, exclusive all. Let's go back here. Exclusive all, if and only if A and B are different. So it means if I use exclusive all here, 0 and 0, they are the same, is 0. 1 and 1, they are same, is the 0, here is 0. And 0 and 1 and 0 are different, is 1. 1 and 0 and 1 are different, is 1 here. Okay. Okay. If I use this one, x and still use x and y, I use exclusive all. So 0 and 1 is 1. 1 and 0 is 1. 0 and 1 is 1. The first are the same, right? 0, 0, they are all 0. Okay. And 1 and 1 are the same, then the last one should be 0. So this is 14. It's 14. Okay. So this is the definition of exclusive all. So I use English exclusive all. Or simply say XOR. XOR means exclusive all in the CS. This is this syntax. So let's say if I use exclusive all, then Z should be 14. Yeah, Z is 14. Yeah. Hopefully I used the above examples to show you the bit operator of the AND or not and exclusive all. Now here are some rules. I talk about the rule for AND. Now I talk about some rule for OR. So any x or 0 is x itself, right? Because if x is 0, then the answer is 0, because 0 and 0 are the same. If x is 1, then 1 or 0 is 1, right? Still x. Right? And I just mentioned about x and 0 is always 0, right? Now x exclusive of 0 is what? Is still say is still x. Right? It's still x. The reason is, say if x is 0, 0 and 0 are the same, so the answer is 0. If x is 1, 1 exclusive of 0 is 1, right? Because they are different. Now, next important thing is x and itself is 0, right? Because exclusive all says if they are the same, the answer is 0. If they are different, the answer is 1. So this is a very important formula. So we can use this formula to do the swap of the two integers. Let's do it. The following code is very tricky. Let's say x equals to 13. I write anything. Y equals to 7. Okay. And now I print out x and y. X equals to x, comma, y equals to y. Now let's do swap. The following code only has 3 lines, but it's very important. Is x equals to x exclusive of y equals to x exclusive of y, and the x is equal to x exclusive y again. Okay, the 3 lines. Now I run it again. So let's see the. So at the beginning, x is 13, y is 7. And next, with the 3 operators, the answer is 7 and 13. The 2 numbers are swapped. How does that happen? It looks like it's very amazing, right? I run the same operator 3 times, and then it becomes swap. Now, I just use the example 13 and 7 and explain what happens here. At the beginning, x, y. Okay. X is let me move here. X, y. Okay. At the beginning, x is 13. Y is 7. Now, first operator is this equal sign is assignment. Is I assign x exclusive of y to x. So this x equals to x exclusive y. So x becomes 13 exclusive of with 7, right? And assign to x. Y I don't change. Okay, this line. Now the second line y equals to x exclusive y again. So it means that x doesn't change. And y now every time x is this, then again exclusive y, which means 13 exclusive 7, right? See this? This is y, because the first x is become this number and exclude y. We can use the associative law, so which is 13 equals 7 equals 7. We can run the next two first. So like and or exclusive or, they are commutative and associative. Okay, so then this is equal to 13 exclusive of 0. We just mentioned about if the two numbers are the same, the exclusive of is 0. And anything exclusive of with 0 is itself is 13. Okay, this is 13. So after this operation, at this time y is 13. Okay. Now I do this again. In this case, y doesn't change and x becomes this one equal to 13, and y is okay. Now because it's not enough space, y is still 13, and x I change a line. X becomes, this is x and the exclusive y, right? Y is 13. So this is equal to, if I can use this number and then 13. I use commutative law and equals to, I can combine the first two first, and it becomes 0 equals 7 and equal to 7. So then I make it as a 7, right? This is 7. So then you can see the two numbers are swapped. So this is a very good example to use the exclusive OR to swap two numbers. Okay. Now this is some rules for the bit AND, bit OR, and bit exclusive OR. Then next, let's talk about the shift. Is the left shift and the right shift actually is a divide or the multiply by 2. Let's do it. I say x actually is equal to x times 2. Okay. If x right, this is left shift and this is right shift. X divided by 2. divided by 0. Now let's make an example to prove that. So suppose x equal to 5. 5 which is 0, 0, 0, 0, 0, 1, 0, 1. Okay. Now x shift to the left. It means what? It means I will make a 0 at the end. So becomes this. So this is 0, 0, 0, 0, 1, 0, 1, 0. Right? I make this 1, 0, 1 to the left by 1 unit. This is 1. Okay. Now this is what? This actually is equal to 10. Right? 1, 0, 1, 0 is 10. Okay. So see this one, 1, 0, 1, 0 is 10. Now, if I shift to the right by 1 unit, it means what? 1, 0, 1 to the right, then this one will be lost. There's only 1, 0. So 0, 0, 0, 0, 0, 0, 1, 0. This is 2. 2 equals to 5 divided by 2. 5, this time, 5 divided by 2, which is the quotient, is not the remainder. So let's prove that. Okay. Now, let's say x equal to 5, y equals to x to the right by 2, and c equals to x shift by the left by 1. So y should be equal to 2, and z equals to x equals to x plus z equals to 10. Right? Y equals to 1. Then plus z equals to plus c. Okay. Oh, that's right. Oh, I missed a semicolon. Right. Okay. 5, this is 2, this is 0. Right. Now, this shift, if you have something, let's say I give an even number, say 6. Okay. So 6, I do this one. If you right shift by 1, and it will be 3. If you left shift by 1, it will be 12. Okay. As long as this even number. 3 and 12 is x divided by 2, and x times 2 as z. Now, okay. So if you want to move deeper, you can think about the negative number. Okay. So if I have a negative 5, what happens here? Okay. That's right. Negative 5 divided by 2 is negative 3. And z is negative 10. So the left shift is always times 2. The right shift is divided by 2. But now it's negative 5. Negative 5 divided by 2. As the quotient is negative 3. It's not negative 2. You think about the y. So which is I will tell you, if you do the quotient, like 5 equal to 2 times 2 plus 1, right? So the quotient is 2. Okay. But the negative 5 is 2 times 3 plus 1, right? So sorry. 2 times negative 3 plus 1. If you think about it in this way, you know the divided by 2. Negative 5 divided by 2 should be negative 3. So we can also like add one more thing is int u equals to x divided by 2. Okay. Let's talk about what is u. Is that the same? U equals to plus u. In this way, if you use divide, it's negative 2. But if you use shift, the negative number is different. So this is 3. This is negative 3. A little bit different. This is negative 3 and this is negative 2. For the negative, is more complicated. And there is one more thing is to shift with the negative sign. So let's talk about another thing. We mentioned about the negative 1, the representation is 1, 1, 1, 1, 1, 1, 1, 1, right? So the highest digit is 0, is a positive number. The highest digit is 1, is negative number. The reason is from the negative representation, use the flip plus 1. So if you do the let's remove this one. Int u equals to x, right shift by 3 greater than equal sign, greater sign. This is shift with the sign. Then u becomes a positive number. U equals to plus u. Let's see what is u. See, u is this number. It's a big number because this is int. It's not byte. It's not byte. This is int. Okay. It's this number. Okay. Now this one, I just want to mention that I don't want to go to very deep. If you want to make a research, you can do the research by yourself. Okay. So when we talk about the bit operator, usually we use the positive number. We don't think about the negative number. And one more thing is to identify the even and odd. Okay. Now let's say again. I just mentioned about the last digit. X equal to 5. This is even. Okay. I can use if else. So I will talk about if else later, but because this is very simple, if x mod 2 equal to 0. Mod is a remainder. If you divide by 2 with remainder 0, means that your even number is 2 times something. So remainder is 0. It's exactly the multiple of 2. Then I print out print x is even. And I use else. I print x is odd. So this is very straightforward. So we can say x is odd. Okay? But I can use another way, use bit operator. I don't use the mod sign. I use bit operator. I can use the 1 equals to 1. So equal is not equal. Equal is assignment. It's not the equal sign. This single equal is assign 5 to x. And the equal is to comparison. So be very, very careful. Equal sign assignment and the equal is comparator. Okay, comparator. They're two different concepts. So I end 1 equal to 1, equal to 0. That is, I compare with the last digit, use the and sign. So if the last digit is 0, then 0 and 1 is 0, then it's even. If the last digit is 1, and the 1 and 1 is 1, then it's odd. Okay, it has the same thing. So there's a I run this with a code because it will think about the last one. So I want to change the precedence. I will talk about it later. So I use execute. 5 is odd. If I change to 6, then 6 is even. Okay. So the equal operator is has higher precedence about the bit operator. So I use a parenthesis to make it as a higher operator. Okay. So this precedence I will talk about later. Okay. But sometimes even I cannot really remember which is higher, which is lower. So I use parentheses to guarantee that this is operator first, and the equal sign is operator second. Right. So sometimes I don't remember that. So in the real project, I can add a parenthesis to avoid some confusion about which one is higher, which one is lower. Right. I think that's all for this session about the binary and the hexadecimal code. And in the next lesson, I will talk about the Java language preferences. Okay. Thank you very much.